Hello everyone, I'm Karthik Kuchar. Today I will be presenting our internal test analysis covering question 17 and 18. This section focus on desecretization and attribute selection. This presentation is submitted to Dr. Shaligram Prajapati. Starting from the slide 1, binning methods. Binning methods. Let's start with question 17. We are given a sorted list of project evaluation scores for 12 students ranging from 5 to 250. Our task is to partition or bin these scores using three different methods: equal frequency, equal width, and clustering. First, we note the total count n equal to 12 and the range 215 minus 5, which is 210. First, equal frequency partitioning. The first method is equal frequency partitioning. The goal here is to have the same number of students in each bin. Since we have 12 students and want 3 bins, we simply divide 12 by 13 to get 4 students per bin. Bin 1 takes the first 4 scores 5, 10, 11, and 13. Bin 2 takes the next 4 5, 15, 35, 50, and 55. Bin 3 takes the final 4 72, 92, 204, and 215. This method is excellent for skewed data but can create odd gaps between the bin edges. Then, equal width partitioning. The second method is equal width partitioning. Here, the goal is to make the numerical range or width of every bin identical. We calculate the width by dividing the total range 210 by the number of bins 3, giving us a width of 70. Bin 1 covers 5 to 74. It contains 8 elements. Bin 2 covers 75 to 144. It contains only one item, which is 92. Bin 3 covers 145 to 215. It contains two items. As you can see, the method preserves the scale but can leave some bins almost empty if outliers are present. The third one, clustering. The third method is clustering. This partitioning data based on natural mathematical distances. K-means K-means algorithm would like separate the data into cluster 1, 5 to 15, cluster 2, which is mid, 35 to 92, cluster 3, high, 204 to 250. This happens because there is a massive jump from 92 to 204, and the clustering algorithm detects that gives a natural boundary. Moving on to the next question, attribute selection. We discussed attribute selection, which is the process of choosing the most relevant variables to build an effective model. We summarized the three key techniques: forward selection, backward elimination, and hybrid method. The first one, forward selection. First is forward selection. Think of this as a building a team from scratch. You start with an empty set, you test every single attribute to see which one performs best. You add that best attribute to your set, then you test all remaining attributes to see which one works best with the first one. You repeat this until adding more attribute stops improving the model. The second one, backward elimination. Second is backward elimination. This is the opposite approach. You start with the full team, every available attribute. You then test removing each one to see which one is the least helpful or most redundant. You cut that attribute. You repeat this process, whittling down the list until removing anything else would actually hurt the model's performance. The third one, hybrid method. Finally, we have hybrid method. This combines the best of both worlds. At each step, you try adding the best new attributes like forward selection, and you also check if any existing attribute become redundant and should be removed, like backward elimination. This dynamic optimization often yields the best feature sets. The final key takeaways are binning. Whether you choose equal frequency for balance or equal width for scale depends entirely on your data distribution. Attribute selection. Techniques like forward selection and backward elimination are critical for simplifying models and improving performance. Third, strategy. There is no single best method. The right choice depends on your specific analytical